Our speaker today will be Levent Alpoge, now from Columbia University, and he's going to tell us about effective height bounds for all degree totally real points on some curves. Go ahead.
Thank you so much. The first thing I want to do is, of course, to thank the organizers. Thank you for inviting me to speak here and speak about this work. And the second thing I want to do is I want to express my admiration to Will Chen, who gave the seminar last week and was so technologically savvy that it inspired me to try to learn how to use Notability on an iPad rather than just scroll through Beamer slides, for example. So that being said, my handwriting, as I discovered, is not anywhere near as good as his. So please complain if you can't read something. It should be pretty legible throughout, but there may be points where you can't read. And actually feel free to complain about anything and ask questions at any point. Interact, please, as much as possible over Zoom. So anyway, I just wanted to start with something light. I always get a kick out of this quote because it's such a formal expression of frustration. The Byzantine scholar Hortasmenos, when going through Diophantus' Arithmetica, got to the problem after the one that inspired Fermat's last theorem in Fermat's reading, and had seen enough, and he decided he must lay down this comment for all time, basically yelling at Diophantus. So this actually has not really much to do with the talk besides the fact that it occurs in the Arithmetica. I just kind of find it funny. Anyway, so let's get to the math. All right, so today we're going to be talking about Faltings' theorem. So just to be clear, I have a number field K and a smooth projective hyperbolic curve. Hyperbolic here means genus is at least 2. Universal cover of the complex points is hyperbolic space. Smooth projective hyperbolic curve over number field has finitely many rational points over that number field. That's the statement. So this was born as the Mordell conjecture and goes back at least to the 1920s. So far back that even Weil worked on it in his thesis years, but was wise enough to submit, quote unquote, just the Mordell-Weil theorem as his thesis, even though his advisor Adamard wanted him to work on this conjecture. And a number of proofs of this theorem are known. So let me just go through them quickly. So Faltings actually, of course, proved this theorem first, but proved this theorem twice in 2 quite distinct ways. This talk is going to follow a bit his first proof, but his second proof, inspired by a proof of Vojta, was very much inspired by techniques of Diophantian approximation, some polynomial method type technique. Bomberi simplified Vojta's proof to not refer to Arakelov theory, just use cookie cutter Riemann-Roch for surfaces. And recently, there's a new proof due to Brian Lawrence and Akshay Venkatesh, which sort of starts along the same path as Faltings' first proof, and then takes a fork into using p-adic methods, which is actually really awesome. And it's actually maybe closer in spirit to techniques that deal with special cases due to Chaboty, which are actually older than Faltings' proof in the 80s. And anyway, of course, there's quite practical methods now known along the lines of Chaboty's method and generalizations due to Mignon Kim, quadratic Chaboty, so to speak, that actually solve literal equations with actual numbers as coefficients. But I want to make the point that each of these methods are ineffective. They do not provide you a finite time algorithm. So in this talk, for the sake of a little bit of laziness, I'm going to just define effective, maybe in the standard way, to just mean something to do with finite time algorithms. So these methods are ineffective in the sense that given your curve, given an equation, and given the number field, of course, going back to Diophantus, you want to find the solutions of that equation. But these techniques do not provide you a way to do it. And remember, I said Faltings' theorem was in the 80s. So let's test out writing a little bit. So I mentioned Diophantus' Arithmetica, and I would be remiss if I were giving a talk about Diophantian equations and I didn't mention the canonical example. So in book 6 of the Arithmetica, Diophantus poses the following question. Solve the equation. Of course, he states this in terms of squares and side lengths of squares, etc. But boils down to solving the equation y squared equals x squared plus x to the fourth, the square of x squared plus x to the eighth, the square of x to the fourth. Non-trivially. Non-trivially. So of course there's a trivial solution where an x is 0 and y is 0. Solve it non-trivially. So this amounts to solving the equation, this equation non-trivially. Yeah, and again, there's a trivial solution when x is 0 and y is plus or minus 1. So this gives you an equation of a genus 2 curve. Genus 2 curve. C over the rational numbers Q. And actually one of the most sophisticated points of Diophantus, historically speaking, is that he understood that rational solutions are also incredibly interesting, not just integer solutions. And I just want to comment that it's actually easy for us nowadays, given Baker's work on linear forms and logarithms, to solve this equation in integers. It's almost should be thought of as immediate, given Baker's work. But solving the equations of the rational numbers, finding all the solutions in the rational numbers is much more serious work. So Diophantus, in the Arithmetica, which is a problem book, states this problem and then goes and finds one non-trivial solution. So he doesn't, at the time, certainly, it was too early to expect him to ask something like find all the solutions, because you have to understand that there are finitely many. That's a real step, and etc. So he asks for one solution, he finds a non-trivial solution. And just to make the point that even with Faltings' proof, etc., it was quite difficult to even solve this one equation. This equation had to wait till Weatherall's PhD thesis in 1998. Berkeley PhD thesis, 1998. Yeah, my handwriting hopefully improves as time goes on. Weatherall's PhD thesis in 1998 determined C of Q. And it turns out that a little exercise in plugging in numbers will have you find the non-trivial solution. And it turns out that non-trivial solution is the only one up to, of course, you can switch x with minus x and y with minus y. And kind of the point is that this is a genus 2 curve. It kind of evidently has a Jacobian that factorizes up to isogeny into a product of elliptic curves. And each of those elliptic curves has rank 1. We would be done if the elliptic curves had rank 0, but they both have rank 1. So the Jacobian of this curve, which is genus 2, is an abelian surface with rank 2. And that's just outside the purview of the Chaboty method. And so Weatherall does a lot of clever things, taking advantage of the fact that Jacobian factorizes to actually determine the points. But anyway, that's just maybe to press on you that it's an art still to solve these equations. Whereas to
you
solve
can tell us what the points are.
I don't remember them off the top of my head, but it's not too hard. I think I wrote them down. Anyway, this is like a canonical example. I don't actually remember them off the top of my head, but I can.
I guess the question is how
not many digits. Yeah, it's something like, you plug in a half or something like that. I don't want to try to do the arithmetic in my head, but you get something like one of them has a 25 in the numerator or denominator, and that's like the largest integer that occurs in the numerator or denominator of either x or y, something like that. But I don't want to try to do the arithmetic on the spot because I'll make a mistake. So I'll tell you what the solutions are. I guess after the talk, if you wait 10 seconds, I can just find it. But at the moment, I don't want to make a mistake. So, but anyway, yeah, Diophantus was able to find them, so they're not too crazy. Okay, so yeah, that's all I have to say about that. Oh yeah, you know what? I should actually say this. There's not really a natural place to say it. Maybe I skipped natural place, but this talk is going to be basically about chapter 9, but also chapter 11, which is just working out an example. So it's chapter 9 of my thesis. Just to say, there's a reference available online at the moment, which works out not just all the details, but maybe too many details. And that chapter, I mean, all the chapters in the thesis are essentially independent of one another, and this chapter does not depend on anything else in the thesis. So if you open the thesis, you might say, oh my God, it's 250 something pages. It's just a bunch of papers stapled together. So anyway, there'll be a standalone version available soon. But I want to kind of jump into the math. So remember, I said Faltings' theorem, and I said that I would be talking about Faltings' first proof. So let's get to it. So Faltings' starting point, step 0 of Faltings. Well, Faltings' paper is titled, oh, Mundell wrote down the solution. Great. 1/2 9/8. Yay. Great. Yeah. So yeah, you do plug in a half. I remember it at 25 somewhere, but I'm thinking of a different equation. Thank you much. Okay, so Faltings' starting point. Well, Faltings' paper was titled "Finiteness Theorems for Abelian Varieties." Of course, there has to be a connection with the Mordell conjecture to prove the Mordell conjecture. And the point is that Parshin had made an observation reducing finiteness statements for rational points on curves to finiteness statements about abelian varieties. That's what we're going to start with. So the point is that there's an amazing construction, much older than either of these papers or observations, due to Kodaira, giving you a family of curves over a given hyperbolic curve. So think of that as map to mg, a non-constant map to mg. So I'll write finite to 1 because we're interested in finiteness questions, just to emphasize these. So, and mg, you can think of as sitting inside ag. So instead of taking the family of curves, you can take the family of Jacobians. And I want to take this, I wrote it like this because I want to take this opportunity to tell you, I'm afraid of stacks. So I'm not going to talk about stacks or points on stacks in the rest of the talk, only here. I'm just going to talk about, if I try to talk about S integral points on AG, for example, I'm going to talk about abelian varieties only, just because, yeah, I'm terrified. So anyway, Kodaira's construction gives you a map, a non-constant map to AG. Okay, and how does this reduce the Mordell conjecture to some finite statement about abelian varieties? This map extends, so let's say this, Kodaira was only working over C, but the map exists for general reasons over Q bar, so over a large enough number field. And this map therefore extends to integral models. Hopefully that's legible. Over an explicit but large finite set of places, S. You could take S to be large enough that you don't have to worry about any subtleties about integral models. So this is kind of the canonical integral model of AG. Oh, I should even say, this is the moduli space of curves. I'm not going to talk about it again, but this is the moduli space of principally polarized abelian varieties. And I'm going to actually also not talk about polarizations in the talk, but because I'm only going to be talking about abelian varieties. So anyway, this is the moduli space of principally polarized abelian varieties, and this is like the canonical integral model over the, if just to be lazy, over the S integers. You don't have to take it over the integers. And this is an integral model of my choosing. I choose the minimal proper regular model. The key point is just that I said the word proper. And so it follows, but just by properness, that the K points, which sit inside the S integral points. So this step, we've made absolutely no progress. This is kind of like clearing denominators. So that doesn't do anything, but they map finite to 1 to the S integral points on AG. AKA abelian varieties over K with good reduction outside S of given dimension G. So this is what Kodaira buys you. This geometric construction of Kodaira buys you that you don't have to think about integral points on your curve anymore. You can just think about abelian varieties.
Are you going to remind us what the Kodaira construction is?
Oof. I don't want to, but I can probably try to remember. I think you do something like you take the curve, puncture. So given a point on the curve, you're trying to produce a curve over your curve ramified with such that the map to the curve. Okay, let me try to say it like this. You're trying to produce CP mapping to C such that this map is ramified only at P.
It's a double covering.
It's no, it's not a double covering, but you can control the degree in terms of the genus of the curve. But just being very quick, you know it's a terrible pi. You know the fundamental, let's just act like I wrote a pi there. You know the fundamental group of this. And what that buys you is that you know how to produce, maybe I shouldn't try this. This is going to take too long and I might screw something up. But the point is that you take a cover ramified only at P, and then you maybe throw in some two-torsion, all the two-torsion points or something like that by taking a large double cover. But I can give you a reference for this because I'm not going to use it. And it's, yeah. The best reference maybe is Brian Lawrence and Akshay Venkatesh's recent paper. But there's also, the way I learned it is there's a paper of McMullen about, I think it's called something like geometric Fermat or something like that. Geometric finite Fermat, something like that. And he does it geometrically, slightly more geometrically. Yeah, great. We have a reference in the chat. Okay, cool. But anyway, there exists a construction. That's the only thing I really wanted to emphasize. But nobody forced us to use Kodaira's construction. Of course, it works for all hyperbolic curves. That's one of the great benefits. For all, you could imagine a different history where Kodaira produced a construction for only hyperelliptic curves, for example, and Faltings' proof would give a finiteness theorem for only hyperelliptic curves, and then someone else goes and finds the general construction. So that's a key point, that it works for all curves. But anyway, nobody forced us to use these maps. So I want to kind of convince you that there are interesting maps besides, or interesting families besides Kodaira's. So okay, let's try to remember how to do this. Do red and maybe this. So this diagram is a diagram coming out of a theorem of Bogomolov and Shinko. Okay, so Bogomolov. I'll state exactly what it says, but it's in a paper about unramified correspondences. So what it says is, if you give me a hyperelliptic curve over Q bar, there exists an atoll cover, C tilde, of that curve C, that admits a non-constant map to this one curve C6, y squared equals x to the 6 plus 1. And this is weird in the same way that Bailey's theorem is weird. At least that's the way I think of it. It's the same level of weirdness. Bailey's theorem about ramified covers of P1 minus 3 points, or ramified only at 3 points. What does it mean for, the reason, I'll explain to you why it's particularly weird. And this is observed in Bogomolov and Shinko. What does it mean for rational points? Let's say this diagram, everything's defined over K. So K is a large enough number field. We're asking, what are the K points of my curve C, my hyperelliptic curve C? Well, by Chevalier-Vey, because I said this map was atoll, there's an explicit extension L over K such that all K points downstairs lift to L points upstairs. Okay, that's just saying that all K points downstairs lift to a bounded degree extension, that's just the degree of this map, of bounded ramification. And that comes from the fact that the map itself has no ramification, it's unramified. And so, this is a consequence of Hermite-Minkowski that L is an explicit extension of K. Okay, so we start with a hyperelliptic curve and a number field K, and we produce this thing, and we say, okay, so these points all lift to this strange atoll cover. But then I can map those points down to this C6. And what does this buy me? This buys me that if I want to know about the K points on this curve, I can just go and try to solve the problem for this one curve. Try to solve Faltings, or effective Faltings, for example, for this one curve over all number fields, keep in mind. Okay, so what this means is that, so to speak, effective Faltings for these hyperelliptic curves over number fields reduces to just effective Faltings, quote unquote, just effective Faltings for this one curve over all number fields. That's surprising in my view, in the same way Bailey's theorem is surprising. Okay, but this curve now admits a better family than Kodaira's. That's the kind of point I want to make. So this is just an aside, but this curve, actually, I don't think this was observed, but this curve is a Shimura curve with level structure. So it corresponds to, you take the 266 triangle group, which is arithmetic, and you take its commutator subgroup, which is index 12. And so this curve is kind of like the upper half plane mod the commutator subgroup. It corresponds to that group. And I said Shimura curve, so the corresponding quaternion algebra is the quaternion algebra of discriminant 6, indefinite quaternion algebra of discriminant 6. And so by virtue of being a Shimura curve, so the curve over Q bar, it's not like this curve, the model I've given you over Q is the canonical model, because Shimura curves don't have real points. But over Q bar, it is a Shimura curve of level structure. And so it admits a very great family of abelian surfaces over it. Abelian surfaces with quaternionic multiplication by an order in this quaternion algebra. Now, I told you I was afraid of stacks, and I wrote universal family. I'd be afraid of writing that if I couldn't construct these by hand. There's a construction by hand called hypergeometric abelian varieties associated to these triangle groups.
So a quick question.
Yes.
So is there how do you see this? Is there some simple trick to see this is that Shimura curve, or you just compute numerical?
Well, the way I found out is I found it in a list of Wolfart, I think. He has a list of small genus Shimura curves with level structure, and this curve, I mean, maybe there was a -1 or something, but up to base changing to Q bar, it doesn't matter. This curve occurs. How do you see this? Well, the way this is actually this is the worst way to see it probably, but this curve admits a map to P1. So, okay, the map is XY goes to, I believe, x to the 6th. So that's a Bailey map. It's ramified only over 0, 1, and infinity, and the ramification degrees are 6, 2, and 6, respectively, over each of the points over 0, respectively, 1, and infinity. And kind of the stacky P1, I'm afraid of stacks, so don't kill me if I use the word stack again, but the stacky P1, where you have multiplicity 1/6 at 0, multiplicity 1/2 at 1, and multiplicity 1/6 at infinity, does correspond to this triangle group. And Takeuchi classified all the arithmetic triangle groups, and you can go look in that list to see that that's an arithmetic triangle group. I guess another way to see it is to just construct the family of abelian varieties, the hypergeometric family, and then just observe. That's actually basically what I do in the example, which I probably won't have time to get to, but you just observe that actually these guys have quaternionic multiplication by this quaternion algebra. I use the 366 arithmetic triangle group, but that's index 2 inside the 2661, just because it has a better curve. The corresponding curve that I deal with has a better model, but it's the same story. You take the commutator subgroup of that arithmetic triangle group, and you get a nice curve. In that case, x to the 6th plus 4y cubed equals 1. I guess 266 shouldn't be that surprising because this is kind of like a generalized Fermat equation. If you clear denominators, you get 2, 6, and 6, z to the 6th there. But yeah, hopefully that sort of answered your question. But the real answer is the way I found out is I just was leafing through a table, and I knew the Bogomolov-Schinkel theorem, so I was like, whoa, this is cool. Okay, so I just want to actually get to the key point of the talk, but it's crucial that I talked about these better families, so to speak, or at least convince you that there are better families in the world, maybe not for all curves. The key point is to use modularity in Faltings' technique. So in Faltings' technique, you reduce to dealing with abelian varieties by using Kodaira's family. And to deal with those abelian varieties, well, you say, for example, there are only finitely many isogeny classes because I know something about Gauss representations into GSP2G. Okay, because Kodaira's construction gives you maybe not so great abelian varieties. But if you want to introduce modularity into the technique, you can't be dealing, at least if you want to do something unconditional, you can't be dealing with Gauss representations valued in GSP2G. You have to kind of improve your situation, and that's where this geometric step of finding better families comes in. So how do you improve your situation? Well, you end up not in AG, but in a moduli space of abelian varieties with Gauss representations into GL2. And for example, the one is a Hilbert modular variety. So a Hilbert modular variety is exactly a moduli space where all the abelian varieties that it parameterizes have Gauss representations valued in GL2. They're GL2 type, so to speak. So we're going to deal with Hilbert modular varieties. And remember, the Faltings reduced to dealing with S integral points on AG. So we're going to deal with S integral points on Hilbert modular varieties. Now, it's unclear. I just want to be straight about this. It's unclear for which curves one can or can't do this. So Hilbert modular varieties, to be clear, say HO, they live inside projective space and are compactified by adding a finite number of cusps. This is the Satake compactification. So the boundary, so to speak, is 0-dimensional. And these are, you could take one to pick a Hilbert modular variety that's 100-dimensional with 0-dimensional boundary. So you can just start cutting by random hyperplanes, by generic hyperplanes, until you get down to a curve. Those hyperplanes will all miss the boundary because it's such high codimension. And that produces tons of complete curves, tons of curves, projective curves that live inside the Hilbert modular variety. Of curves inside these varieties. And so this technique will tell you about their rational points, but this is just an existence statement that I've given you. And I had to work pretty hard actually to find an explicit curve for which this study of S-integral points on Hilbert modular varieties tells you something. So it's not clear to me which curves, for example, it's not even clear to me over C, which curves map to Hilbert modular varieties in a non-constant manner. So anyway, that's the downside. So let's get to the integral points on Hilbert modular varieties. So like I said, Faltings was dealing with AG of OKS, S integral points on AG. And here we're going to deal with, this is supposed to be slightly calligraphic or something. S integral points on these Hilbert modular varieties for the same reason. We want to deal with rational points on curves. We imagine the curve sitting inside the Hilbert modular variety with no punctures or anything. Like the whole curve sits inside, the complete curve sits inside the Hilbert modular variety. And so we can reduce to the study of S integral points on the Hilbert modular variety, and that's what I do here. Okay, so the setup is the following. It's basically going to be, it's going to end up being that you can find an effective height bound on the S integral points in the Hilbert modular variety, so long as something holds. So, and in a second, I'm going to tell you exactly that this sort of theorem. It's not new if you work over Q. And in fact, the idea of using modularity also not new. So it's really just a technical improvement, just to talk about rational points on curves. So, okay, here's the key hypothesis. K, your base field, the field of definition of your abelian varieties, should be totally real of odd degree. Okay, so what am I talking about? Just to be clear, I'm talking about, so I have an order in a totally real field F. That's going to be the ring of endomorphisms. I have an abelian variety over K with good reduction outside S with endomorphisms by O. Actually, the classical way of saying this is with real multiplication by O. So something just changed. Let's change to the eraser. Dimension A should be degree of F over Q. So this is called being GL2 type over K. Crucially, the endomorphisms are defined over K as well, so that the Gauss representation actually lands in GL2. Okay, so the statement of the theorem is that such abelian varieties satisfying exactly this. Good reduction outside S, aka bounded conductor, abelian varieties over K that have real multiplication by O, have effectively bounded height. But the crucial point is that you're working over a totally real field of odd degree. And so that's the statement of the theorem, an effective height bound on the points. So, okay, actually slightly more than the points here, because the points here, there's some condition about polarization. This is literally the theorem, this statement. Okay, so what did I want to say? Oh yeah, anybody who's worked with Hilbert modular forms and abelian varieties associated to them will immediately recognize why I needed this hypothesis. Okay, so I need to talk about Hilbert modular forms. That's why I say totally real. But the fact that I have odd degree is exactly because I need to be able to construct an abelian variety associated to a Hilbert modular form of parallel weight 2. Maybe I should say Hilbert modular eigencusp form of parallel weight 2. Yeah, but anyway, this statement about abelian varieties, I promised you I wouldn't talk about stacks. So this is actually a statement about abelian varieties, implies that there's an effective height bound on the integral points on this Hilbert modular variety. I guess just for completeness, maybe I should say this is the Faltings site. Yep.
Oh, so in the case where F is Q.
Yeah, I'm about to get to that. It's already been done, yes.
But you don't need the purple hypothesis in that case, right?
Well, if F is Q, if you're talking about elliptic curves, yes, you don't need any hypothesis. Actually, I was going to get to that too. So
okay.
Yeah, just to like kind of understand what's going on. Let's say F is Q, so O is Z. So the dimension of A, because F is Q, is 1. So we're talking about elliptic curves. And we're talking about, so this is no condition. We're just talking about elliptic curves over K with bounded conductor. That's equivalent to saying they have good reduction outside an explicit finite set.
Mm-hmm.
That is a problem solved by Baker.
Yeah,
I think maybe Shafarevich.
But so the proof you're giving is something is is different from,
Yes,
you're
most
not
definitely.
using
Yeah.
Baker's method.
Yeah, yeah. I mean, the point there, maybe super fast, is you don't need any hypothesis on the number field. And why is that? It's basically because to say that you have bounded conductor is reducing you. So what it's saying is that the discriminant. So if you're talking about an elliptic curve, you have y squared equals x cubed plus ax plus b, and it says that the discriminant of that cubic has primes, involves primes only inside S. And the discriminant is of the form, forget about constants. The discriminant is of the form x cubed or a cubed minus b squared. So you're actually just solving an equation of the form, replacing b by y and a by x. You're solving an equation of the form this, which is another elliptic curve, except you have to talk about S integral points on this elliptic curve because you allow like to get down to finitely many n. But anyway, this is, I think, Shafarevich's argument using Baker.
Yeah. I'm just pointing out that
Yep.
you don't need the purple hypothesis when f is equal to q. So,
Yeah, that's absolutely correct.
but
Yeah.
so your argument is different. So you're.
Yep.
Okay. No, I thought you said that the argument was the same when.
As Baker's, no, it's the same as what I'm about to say. It's the same as Hector Poston and Murti and Raphael von Connell's arguments. So it's the same, except there's like you have to do some technical improvements, but the underlying argument is by modularity. And I'm going to show you guys. But
Effective here means that you can just do this in principle, right?
Yes, I don't write down. That is a definite difference between Raphael von Connell and Hector Poston and Murti's work. They write down a bound. It's explicit. Whereas this is just there. You can in principle compute the bound, but I don't try. It looks painful. Is the point. Over Q is practical. Yeah. Yep. And that's you could get a lot of very practical corollaries from their work over Q. Yeah. Anyway, so the height is Faltings height, and in the case of elliptic curves, you can use different techniques because elliptic curves are simple enough. But okay, so yeah, that's the next thing. So I wanted to say
another thing is it's not that only that the modularity is not known in general, say the degree is not. It's the search of an abelian variety that's underlying it as well, right? So I mean, if you knew Langland's conjectures, this wouldn't help you.
Yeah,
directly.
You need to know constructions of motives because. So here's the point. I could have said if I were just using modularity, I would have said let's work over a CM field, because actually at the moment modularity is now known over in the way that I need it is known over CM field. But to get a height bound, I also need to construct. I'll show you the argument in a second over Q. But anyway, yeah. So I just want to say Murti and Poston did this over Q for elliptic curves, and they get very good bounds. And like very, very practical bounds. And Raphael von Connell independently and simultaneously, I believe, did this over Q and for general rings of endomorphisms, also getting practical bounds. And both used modularity. So like we said, there's an argument for when you work for elliptic curves due to Baker, but the bounds you get are kind of horrible, probably. And Murti and Poston made it practical. But these guys, another point is that these guys came up with an argument that actually generalizes in a very positive way, whereas Baker, you're stuck with working with elliptic curves. Okay, so
I think it is actually practical to use Baker's method because you can reduce it to S unit. I mean, that's what people actually do, I think, when they're computing these lists of elliptic curves with good reduction outside the first 5 primes or whatever.
I defer to Hector because he's definitely more of an expert in the practicality than I am. But yeah, you guys, I'm interested to hear which is maybe more practical because you guys actually do the computations, whereas I'm not saying it's
more practical. I'm just saying it is practical, and so
yeah. You have to be pretty clever when in sieving, I think, to get Baker's bound down to something usable. But it's true. I shouldn't imply that using Baker's linear forms and logarithms gives you totally impractical bounds. I mean, you can actually find integral points on all sorts of hyperelliptic curves by using Baker. Yeah, so I wanted to just show an argument that occurs in Raphael von Connell's work that I refer to as the Master-Wusthof / Bost argument. Okay, so the setup is you're given an abelian variety over K, general number field, and so given want all B over K such that there exists a map. So want all over K. So just in words, you want to find, given A, you want to find all isogeny factors of B. Oh, sorry, of A over K. All isogeny factors of a given abelian variety over K. Okay, so how does this work? So Poincaré, complete reducibility implies that A is actually isogynous to B cross C for some C. We don't know anything about C. Maser-Wustholz, oops, switch to the eraser. Maser-Wustholz, and actually to be precise, and maybe to try to be fair, Raynaud and Maser-Wustholz proved bounds that are just suffice for this. So Raynaud, in the asterisk volume after Faltings' proof, works out an explicit isogeny estimate, so to speak, and so both suffice for this argument. So an isogeny estimate tells you that you can bound the height of B cross C in terms of A, in terms of the height of A. There's actually an explicit formula. In principle, I could have written down to the Gaudron-Raymond, but I didn't think it would be that enlightening. But you should think of this as totally explicit. You just plug in the numbers. So you can bound the height of B cross C in terms of A. So what that means is you can find all isogynous abelian varieties to a given abelian variety just because of these isogeny estimates. And that looks pretty good. That's supposed to be a B, sorry. That looks pretty good because the Faltings height of B cross C is the height of B plus the height of C. I'm going to actually erase that because it just looks so bad. Okay. And it looks good because, heights are supposed to be non-negative, but the Faltings height, it can be negative, but not that negative. So Bost's lower bound. The height of C is at least some constant, minus some constant times the dimension of C, and you can bound the dimension of C by the dimension of A, for example. So this is Bost. And what results is that you've bounded the height of B just in terms of A. There's two terms, and they both are just depend on A. So the upshot is that you can find all the isogeny factors of a given abelian variety in finite time. Okay, so having that statement in mind, the specifics aren't so important. It's just that you can effectively find the isogeny factors. Let's find all the elliptic curves over Q of conductor N. Well, over Q, modularity implies that elliptic curve over Q of conductor N is an isogeny factor of the Jacobian of x naught of N. This is kind of the geometric way of stating modularity. So given N, you write down the Jacobian, this J naught of N, and you use the Maser-Wustholz-Bost argument to produce a height bound. So the height of E, how did that happen? Anyway, try again. So the height of E is explicitly, effectively bounded. And that's the sort of argument that generalizes that von Connell uses in his paper, and also actually basically the sort of argument that Murti and Paston use, although they use different techniques, but it's the same sort of idea. The curve is an isogeny factor of J naught of N. So that's the argument, just given the Maser-Wustholz-Bost argument. And the proof of, I'm going a little maybe fast through this, but hopefully, yeah. Oh, I should say, this is the key point where I explained that not just modularity suffices. So modularity is not really a statement about, it's not really a statement about anything geometric. It's just saying that the L function of the elliptic curve matches the L function of a weight 2 modular form. And just for local reasons, because Galois representation is matching up, the level of this modular form matches the conductor of the elliptic curve. Okay, so that's where this N is. N is the conductor. So this is modularity. But there's a construction of an abelian variety associated to a modular form of weight, holomorphic modular form of weight 2. Maybe I should say new form of weight 2, due to, I think, Shimura. But anyway, definitely classical. And that is the statement. The combination of these two statements is what's used in deducing this geometric statement. Faltings proved the Tate conjecture for H1 of an abelian variety, which implies that E and this abelian variety are isogynous. And this abelian variety is constructed as an explicit quotient of J naught of n. So it follows, because these two are isogynous, that E is also a quotient of J naught of n. So that's kind of the explanation of the two steps. Yeah. So now I'm going to move on, because I just want to show you the theorem, proof of the theorem assuming modularity. Assuming modularity, that's key. Modularity is not known. So the crucial point over Q is that Sayre's conjecture is known. So you actually know that all elliptic curves over Q are modular, whereas over a general totally real number field, or even if it has odd degree, whatever, modularity is not known. And the proof of this theorem, assuming modularity, simplifies a whole lot. But this is like the crucial argument that we use. So you no longer have J naught of n, which was the kind of abelian variety, if I use that adjective correctly. But you now replace it with the Jacobian of an explicit Shimura curve with level structure. And so in this case, modularity implies that all your abelian varieties are quotients of an explicit Shimura curve with level structure, are isogeny factors. And so by the same argument, because of modularity, which I'm going to explain to you how it applies this geometric statement, the height of A is effectively bounded. Okay, so here, this L function thing. So modularity only tells you a priori an equality of L functions between, so, okay, here I mean, because A is GL2 type, just to be quick, A admits a degree 2 L function. So it admits a Galois representation valued in GL2. In fact, maybe I should say it. So let's just say you have a compatible family of Galois representations. Okay, to GL2 of O lambda, where O is that ring of endomorphisms, and you have a family, let's say rho lambda. So you can form a degree 2 L function. That's this 2. And modularity says that modularity would say that all such L functions actually come from L functions of parallel weight to Hilbert modular forms. Maybe I should say Hilbert modular eigencusp forms. That's all that modularity gives you. But here again, because I'm working over a field of odd degree, there's a construction of abelian varieties. This time, I believe, but maybe I should have checked this more carefully, but I believe it's due to Hita. There's a construction of an explicit abelian variety with matching L function, with matching degree 2 L functions. This abelian variety is also of GL2 type, and it's an explicit quotient of the Jacobian of an explicit Shimura curve. And here the point is that here's where you're going to see odd degree. So you take your Hilbert modular form, you're trying to construct an abelian variety, you transfer it to an automorphic form on a quaternion algebra. Well, I didn't assume anything about the Hilbert modular form to begin with, so I can't transfer it to a quaternion algebra which is ramified at a finite place. So the quaternion algebra has to be unramified at all finite places for me to have a chance of doing this in general.
It's Jacquet-Langlands, not a.
Yeah, you Jacquet-Langlands transfer. I should have said just not transfer, but Jacquet-Langlands transfer. Yeah, you Jacquet-Langlands transfer, and I want to end up with an abelian variety. I want to end up with this Galois representation, the Galois representation of this Hilbert modular form in the cohomology of in H1 of something, so H1 of a curve. So if I want to end up with a curve, I need the quaternion algebra to be ramified at all but one finite place, infinite place, all but one infinite place. So it's unramified at all finite places, and it's got to be ramified at all but one infinite place, because the dimension of the corresponding Shimura variety is going to be the number of unramified infinite places. And for such a quaternion algebra to exist, that set of all but one infinite places has to have even cardinality. That's exactly where I use that the degree of the field is odd. And then actually, it's not known unconditionally how to construct an abelian variety if the degree of the field is even. This is maybe it's called the existence conjecture or something, but it's not. It's known under the absolute Hodge conjecture. But yeah, anyway. So I just want to say, because modularity is not known, we got to get away with using something weaker that is known. And potential modularity is known in this context. We're over a totally real field. All these abelian varieties maybe are not modular over K itself, but they are modular over some totally real extension of K. And that is a theorem of Taylor's. So we need to understand, if we're going to use that, exactly what this argument gives. The argument gives a height bound if we can produce an explicit finite set of extensions over which any abelian variety we're interested in, one is modular over one of those extensions. So you just got to, so if we can produce ahead of time, we say, okay, I'm given these parameters O, K, and S, and I'm trying to look for abelian varieties that are good outside S, etc. We need to produce ahead of time an explicit finite set of extensions such that we know that any abelian variety we are interested in, again, is modular over one of those extensions. And then we can run this argument, this height bounding argument, over each of those extensions, take the maximum of the height bounds that come out, because we're sure that this argument will work for each abelian variety over one of those extensions. So in other words, we have to control what comes out of Taylor's potential modularity theorem. Okay, so I've already said that every abelian variety is potentially modular. And this is a theorem due to Taylor, sorry, but there's a paper of Snowden that I guess learned it from, but also learned a very key trick from, to kind of keep the extension being odd degree. Okay, so I'm gonna, the first point that has to be observed. So we're now asking ourselves, what does Taylor's argument produce? Given an abelian variety A, so the way Taylor's argument sort of goes, I'm simplifying a lot, but trying to keep the key points. You choose a lambda such that the residual representation, the mod lambda representation into GL2 of O mod lambda, has large image. Large image here means SL2FL. Let's say lambda divides L. L is the rational prime underneath lambda. So it has image containing SL2FL. That's what's meant by large image, let's say. All but finitely many primes satisfy this hypothesis. However, the estimate that what I just said, all but finitely many primes satisfy this hypothesis, that general statement comes out of Moser-Wustholz, or comes out of Faltings' isogeny estimate. So we can't just say that and use that a priori bound, because that estimate depends on the height of the abelian variety, and we're looking for the height of the abelian variety. So we've got to be more careful. But we will be more careful. So anyway, but just to understand what happens. So you choose a lambda for which the residual representation has large image. This is kind of like the Taylor-Wiles hypothesis, if that rings a bell. So I'll call the residual representation rho bar. The key point is the extension produced by Taylor's argument only depends on rho bar. It doesn't depend on the lambda-adic representation. It depends on the residual representation only. Okay, so that's one key point. That's not actually the truly key point, but we would be dead if it depended on the full lambda-adic representation. Okay, and now we need to understand, given rho bar, so let's say we have lambda and rho bar in our hands, and we're just trying to figure out, how does L rho bar depend on rho bar? How do we produce it? Given rho bar, we can determine L rho bar as follows. We just follow Taylor's proof, and Taylor's proof is explicit except for one step. There's a step where you say, construct a moduli space of abelian varieties again, and we call it X. And I'm going to simplify just to summarize why Taylor has to do this and what he does. So let's act like the only question, let's take as a black box modularity lifting theorems and act like the only question of modularity is whether or not your residual representation is modular. So long as you can get your residual representation to be modular, let's act like that implies automatically that your full representation is modular. Okay, so we would love for this residual representation to be modular, but a priori it's not. And so Taylor's amazing idea is, let's produce an abelian variety with residual representation at this prime lambda equal to our residual representation, and residual representation at some other prime coming from a theta series. If you could produce an abelian variety like that, then you'd be modular by the following argument. Well, the mod P representation is modular, so the p-adic representation is modular. P-adic representation modular means that because they have the matching L functions, means the lambda-adic representation is modular of this other abelian variety. So the mod lambda representation of the other abelian variety is modular, but the mod lambda representation of the other abelian variety was our mod lambda representation. So that, again, our abelian variety is modular because we got the mod lambda representation modular. Okay, so that's Taylor's argument in a very simplified form. So he writes down a moduli space of such abelian varieties. And by what I just said, we would be done if that moduli space had a K point. But, unfortunately, who knows if that has a K point. But Taylor's great realization is it's easy to show varieties have totally real points. the question of whether or not a variety has some totally real point is a local question only. That's one of these positive results towards Hilbert's 10th problem over so-called large fields. So he uses a theorem of Moret-Bay, but it goes back to Rumley, and before that, the beginning theorem in the subject is Fekete and Sego's theorem, and then for totally real algebraic integers, Raphael Robinson's. So the point here is just that
that's effective.
Yeah. Well, okay, yeah, I'm gonna. Yes, I'm about to say, yeah. So what I want to just say, Taylor's argument produces some totally real extension, which you may as well, by taking a Galois closure, say is Galois. So it basically amounts to the statement that if this variety has a point over this extension, then because of this prime switching argument that I just sort of described, this guy is modular over that extension. But who's to say? We need the totally real extension to have odd degree to run this Jacquet-Langlands transfer business. So who's to say that this field has odd degree? Nobody. I just took a Galois closure, so it has, for all I know, degree some factorial. However, this is the argument I learned from Snowden's paper, which is really cool. So L rho bar, I wrote tilde for a reason. L rho bar is defined as the fixed field under A 2 CeLo, because I took this to be a Galois extension, a 2 CeLo of L rho bar tilde. So it should be a bar. So this definitely has odd degree, because it's the fixed field of a 2 CeLo. All the 2's are gone. However, by solvable descent for GL2, which is due to Langlands, modularity over this solvable extension. So L rho bar tilde is a solvable extension of this guy because any 2 group is solvable. So by solvable descent, if you're modular over the solvable extension, you're modular downstairs. So that's how you keep the degree odd. So anyway, this has odd degree and has the property that this abelian variety is modular. Okay, so that's solvable descent. That's one of the key points. Okay, so and I have to say, so how do you find L rho bar tilde? This once you find this field over which this variety has a point, you're home free. As I just said, you take a fixed field of 2 CeLo, etc. So how do you find this field? Well, here's the lazy way of doing it. You could do better and be more explicit. The lazy way of doing it is to just say brute force. Write down, this lives inside some projective space, this moduli space, and start brute forcing coordinates. Just plug in all these algebraic numbers of larger and larger height, maybe totally real algebraic numbers of larger and larger height. And Moret-Bay's theorem says you're going to stop at some point and find a point. This is the proof that a recursively enumerable and co-recursively enumerable set is recursive. So, Professor Sarnak doesn't like that, but I know. But you can be more explicit. You can go into Rumley's argument, which Moret-Bay relies on, and actually derive estimates. But for the purposes of a talk, for the purpose of convincing you, brute forcing certainly suffices. If you have some way of enumerating the elements of a set, and it's yeah.
Can you remind me? Are you for the whole argument? Do you need to do this for just one x or finitely many x, or you
1x? Yeah, 1x.
1x. Okay.
Yep. You start with rho bar and you produce another prime as you wish, and produce a residual representation, which comes from a theta series, and then you write down the moduli space associated to both of those.
Okay.
It's another Hilbert modular variety.
So k is fixed, and you have your x.
You have your x. Once you have rho bar, you have x.
Yeah, okay. So you just need to find a point on one variety. Okay.
On one variety, exactly. And you just brute force is all I say.
Yeah, I don't like this brute force, as you said. Yeah. Anyway, more importantly, call me Peter now.
Okay. Peter, and Peter doesn't like it either. Yeah. So great. But anyway, yeah, there's one variety, but the crucial point is I haven't gotten to the point where I say, how do you determine all the rho bars? I just said you start with rho bar and you can produce these extensions. Well, we got to know what we can produce the rho bars, and that really boils down to bounding lambda. So here's the point. So I said it boils down to bounding lambda, so I'm going to deal with lambda now. So I said that finitely many lambda don't have large image, residual representation with large image, and that estimate in total generality comes out of the Moser-Wusthof theorem, for example. But we're not in total generality. We're working with Galois representations valued in GL2. And I chose to use a lemma of Dimitrov, but this is it's the sort of statement. So okay. So here's exactly the statement. Once lambda is explicitly sufficiently large in terms of the parameters, actually the residual representations all have large image, every one of them. But it's actually easier. It would have been easier for me to just say a density 1 subset of residual of how to say this. Maybe I shouldn't say the weaker statement. I'll just deal with this. So this is a lemma of Dimitrov's, or a proposition, I guess, of Dimitrov's, dealing with Hilbert modular forms and their residual representations. And really what this is about is, let's just take the case over Q of just the Ramanujan delta function. You're asking, does the Ramanujan delta function have any interesting congruences mod this really big prime? And it's known what a criterion is for the Ramanujan delta function to have an interesting congruence. And it's totally classical that well, anyway, it goes back to Sayre from long ago, that it doesn't have interesting congruences past a certain prime, an explicit prime. And that's the sort of question that you're answering. It's one of these classical questions about congruences. So Dimitrov worked it out, or did it for Hilbert modular forms, with a really cool argument. But his end game has one argument which is not explicit, so I had to change that slightly. And also, he's working with Hilbert modular forms, whereas I'm working with Gauss representations coming from abelian varieties. But thankfully, his argument actually is just using the fact that the Gauss representations that are involved with Hilbert modular, that come from Hilbert modular forms, have certain Hodge-Tate weights and integrality properties of traces, things that hold for these abelian varieties. So anyway, I could have used a weaker theorem, which just guarantees not all primes larger than an explicit number, but a density 1 subset of primes having large image. But anyway, so that's how you deal with the prime. So let me write it like this. So step 1, basically, so step 1, you choose lambda. Okay, so you can choose lambda because you have this explicit bound, so you just choose lambda sufficiently large. Step 2, for each row bar, and I haven't told you why I can loop over the row bars, find L row bar by doing the Taylor argument. So why can I loop over row bars? That's much easier. That's just Hermite-Minkowski. The possible residual representations, let me just write exactly what they are. Gauss over Q bar over K, GL2 of O mod lambda. I chose lambda, remember? So this has bounded cardinality. So I have lambda in my hands, and there's a formula for the cardinality of this. This residual representation essentially amounts, up to some explicit finite choices, to giving a number field, namely the fixed field of the kernel of the representation. This number field has bounded degree because its degree is the cardinality of the image, and the image is of bounded cardinality. And it has bounded ramification because this residual representation is supposed to come from an abelian variety with good reduction outside S. And to say that an abelian variety has good reduction outside S is exactly to say that its lambda-adic representation is good outside S, and I guess maybe I should say outside the norm of lambda. It's unramified outside S and the norm of lambda. That's the easy direction of Néron-Schaffer image. So in other words, the lambda-adic representation is unramified outside S and norm of lambda. So in particular, the residual representation is even more unramified outside S and norm lambda. So this number field, this extension of K, is a bounded degree in ramification, so easily determined by Minkowski's proof of the Hermite-Minkowski theorem. And that's how you find the row bars given lambda. Yeah, and I mean, I should also say the row bars, they should be odd and such, but these are not difficult conditions to guarantee from after this argument. So anyway, by doing this brute force or cleverer, I knew that Peter would not like the brute force argument, so I wrote or cleverer here. Just by doing the brute force or cleverer, we produce this finite set of extensions, and then you go and you do the Moser-Wustholz argument to get the height bound, and that's it. Thank you.
I mean, there's a reason. Oh, sorry.
Go on. I just want to say questions.
Okay, so there's a reason I don't like that argument, because it says that you have an effective bound in the sense that you run an algorithm and it must end, but you don't sort of a priori tell me when it's going to end, which you can do.
Yeah.
That's right.
Yeah. You can definitely do it. I mean,
In
you
other
have
words,
to work
in
hard.
principle, you could write a number down for the height. I think there's a big difference. Between saying something has a height bound, that you could write a number there, or that you're running some kind of machine that has to end because some conjecture. It's just a matter of making Rumley stuff effective, right?
Yeah. So that's the key point. The key point is, actually, let's go back to Fekete and Sego. Fekete and Sego is about sets with capacity bigger than 1 having lots of algebraic integers, having all conjugates in the set, right? And the key point is, what does it mean to have capacity bigger than 1? It means that some integral, like integral over your set, maybe it's like dx, dy, and then there's like a log, maybe minus log, I don't remember, 1 over x minus y, something like this, that this integral is negative. Sorry, there should be not dx dy, that's the whole point. Sorry.
Yeah, but it's something that you can effectively compute from the set, right, which you have in your hands.
So, well, yeah, this is the painful point. So you're integrating over your set, and there's a measure in your set.
The
I remember,
equilibrium measure. Yeah.
The equilibrium measure, exactly. So the equilibrium measure is what's giving you the logarithmic capacity. And for this integral to be negative, which is what having capacity bigger than 1 means, is to say that there exists a measure, the equilibrium measure, for example, for which this integral is negative. So if you approximate, and this is what Fekete and Sego do, they say approximate this measure by a sum of delta masses well enough that the sum of delta masses, when you integrate like this, taking the sum of delta masses to be your measure, also has negative integral. Negative, I guess I should call it energy integral or something.
And then you can use those points, yeah.
And then you use those points to, then you start producing things in terms of those points, because it's something about polynomials. But you need to know something a priori about the equilibrium measure to approximate it by delta masses. That's the point that looks painful that I was maybe too lazy to do.
So but you should definitely do it because, and then I have another question.
Yeah.
You don't write any numbers down, and most people who work in effectiveness are very proud to eventually produce numbers. Where in your arguments would you think the worst? I mean, your bound's going to be worse than the inverse Ackermann function or something.
It's going to be horrible, yeah.
Where in your argument do you think you'll be worst, weakest?
Probably here.
Right there.
Yeah, I mean, everything else is actually quite, the bounds are not, I don't want to say good. Good from the perspective of like a guy who grew up with a baker, so to speak. These bounds are not like e to the e to the e to the e to the something. They're not horrible bounds, but the bound that will come out of this, I think, will be terrible.
Well, that's interesting.
It's going to be Ackermann, though. I think.
Yeah, it's not going to be inverse. Yeah.
It might be just.
I was kidding.
Yeah.
But nobody's ever tried to make this effective, as far as you know.
Even Fekete Sego, they haven't tried to make it. As far as I know.
Yeah. Okay.
Yeah, as far as I know.
Do you check Yulumo and his student?
Who? Say again?
Yulumo and his student work on this Mohi-Bayes theorem effective. But you can use my theorem.
I didn't know that. Yeah, I didn't know. So I should say this. It is true that the only question. So Rumley gives an upper bound on the heights.
Yeah, I mean Rumley uses and Chimberg is a capacity, but I have a theorem called successive minima.
Yeah, So I think what I'm going to say is relevant.
I never done that, but probably some student of Yulumo or TCA, did he do something like that?
Let me translate him. He's saying Ulmo firstly.
Yeah. But I didn't know. What I want to say is Rumley. So Rumley gives an upper bound on the heights of the points that you produce, but not their degrees. So the question, and it's the same with Fekete Sego.
Oh, you want a degree? You want an effective
degree as well? Yeah, you need both.
You have to.
That's the point. Yeah. So like with Fekete Sego, of course you get an upper bound on the height because you know that all the conjugates live inside the set E. But you don't know it. So the normalized height, I should say. But you don't know anything about the degree, and that's where this whole approximating by delta masses, etc., comes in.
Then my work doesn't work.
Well, yeah, that's the you have to fight for that, and I don't. I didn't want to.
Okay.
Actually, I should have said this during the talk. I want to take a moment. It's irrelevant. I'll scroll back down. I just want to take a moment because on the internet, it seemed like there was a little bit of confusion about this. Okay, so what we're used to when we're talking about effectivity is we can't determine the set itself, but we can at least give an effective upper bound on the size of the set. right? But Faltings' proof of the Shafarevich conjecture does not even give an upper bound on the size of this set. You use cleverness to get an upper bound on the size of the set of rational points. Raynaud, for example, I think Raynaud or Spiro, one of the two, use a repulsion argument in this asterisk volume I mentioned already to get an upper bound on the size of the set of rational points, but it doesn't come from an upper bound, an effective upper bound on the size of the set of abelian varieties with good reduction properties. Okay, I just wanted to make that point. So we're used to the statement that we can upper bound the sizes of sets, the number of exceptions of something effectively, but we can't actually determine them that easily. But actually, in this case, nobody has an effective upper bound for the size of this set. Fun fact. It's not relevant to our discussion. It's just I remembered that I forgot to say it.
And the other thing you didn't, maybe, I know what you've done, but you have this theorem about S integral points on these Hilbert modular varieties, and the application is to any curve that you could put. Okay. So maybe your final theorem.
I tried. Oh, it's cut off at the bottom. I didn't know. Oh man, I didn't realize. So I see something down here, a little further than what you guys see. I didn't realize it was cut off. Sorry, due to Zoom. But anyway, I hope I didn't actually write down there and nobody saw it. But anyway, yeah. So I realized I probably wouldn't get to the slide, so I kind of tried to put it in a way that you could see everything I had to say. But yeah, the application. I had to work for this, but you can produce a family of twists of a given curve, of some curve that I found. X to the 6 plus 4i cubed equals 1. And it's the same sort of story as what I said with the 266 arithmetic triangle group, except when I was talking about the Bogomolov-Chinkel curve, I was talking about a model over Q that wasn't like the canonical model, whereas this is, I want to say the canonical, I mean, it's not the canonical model, but anyway, the point is that the family of abelian varieties you write down, which are quotients of the Jacobians of desingularizations of these curves, where F is a Bailey map. It's an explicit Bailey map. It's just X to the 6th again. You can just write down all the families, everything explicitly, and you observe that this hypergeometric family of abelian surfaces is GL2 type over your base field. So you can apply the previous theorems about abelian varieties. But I mean, the point is just to find an explicit curve. I didn't find this explicit curve by saying, go compute an equation for a Hilbert modular variety and then do the cutting procedure. And then now you have an explicit curve inside there. Yeah. So that, yeah, I still haven't found a curve in that manner at all. But I kind of stopped trying because of this curve. Sorry. Yeah, it's a bit strange. Equations for Hilbert modular varieties are not known precisely enough to find their how to say this? Like birational models are known. And then another problem is when I say Hilbert modular variety, I really mean Hilbert modular stack. So like they are hyperbolic. So for example, there are rational. If you ignore the stack structure, you can produce ones that are rational, which obviously can't happen if they're hyperbolic. So people tend to, I guess, take the coarse moduli space is the right phrase to say, and that is not sufficient for me because I kind of want to get curves, hyperbolic curves out of it. And anyway, it's just me complaining about what I found in the literature. But
I just have a comment about the Bogomolov-Chinkel result.
Yeah.
So
I should have said.
I wouldn't call that. I'm just saying I wouldn't call that a belly-like result just because it's. I mean, this is a purely this particular theorem is just a purely geometric result. You could take any curve, any hyperelliptic curve over the complex numbers.
I didn't know that. I didn't know that. I didn't read their proof that carefully. So I thought it relied on Bailey's theorem. I didn't realize. You're right. Okay.
They use that elsewhere in the paper, but not.
I see.
This resulted just a particular. If I remember right, it's like a degree 72 cover of your curve, and it just always has.
I see. Yeah. So you're saying by virtue of being hyperelliptic, you have a finite set of points to kind of play with, and they just play with those points. You have y squared equals f of x, and you have the roots of f of x, and and they just deal with those points directly. You don't need a abelian map.
You can do this construction even in a family. You can do this. You can have this. I mean, you can first do some. I mean, they first do a little reduction to go from any hyperelliptic curve to take a to go to the genus 2 case by just choosing a degree 6 factor of the right hand side, and then once you have it in genus 2, then you can just do it. You can do it universally, and so.
Yeah, I'm a bit confused. So you ask, but C6 has only countably many covers, right? By Galois theory, it's a dominant.
Yeah.
But you have uncountably many C.
Sorry?
You have uncountably many.
If you work over the complex numbers, you're saying.
Yeah, there are uncountably many C. That's true.
But C6 are only countably many coverings.
No, yeah, but C well, no, because the cover of C6 is not required to be étale.
Your ramification. Not necessarily étale. But maybe ramification not necessary to be rational, right?
Yeah, they don't have to be defined over Q bar.
Okay. So you're covering.
I see.
So you can find a family, like an algebraic family of covers.
I didn't know that at all. I see. I always thought of it as weird, like Bailey's theorem. You're right. So I shouldn't have said that. Actually, now that you mentioned it, so Bjorn actually proved a theorem much stronger than this using their theorem. So instead of just saying hyperelliptic, I could have said solvable cover of P1. So hyperelliptic curves are solvable covers of P1 because they're Z-mod 2 covers of P1. But more generally, you can do this construction for any solvable cover of P1 to end up with C6. It's a really cool theorem. And yeah, anyway. I should say.
Maybe we'll officially end this seminar for the moment. And thanks, Levent.
Thank you.